So let's dive right in. The goal of this video is to try to bridge the gap between some of the theory behind exercise 5 in the IBM Quantum Computing Challenge 2021 and some of the theory behind it. So if you were anything like me, you might have been super eager to learn everything about the theory under everything that we were doing. But due to time constraints or whatever else, to some degree, you might have just kind of played around with the code with a superficial understanding of what might have been going on underneath until you got the answer you were satisfied with. That might be true to various degrees for people. Some people might have just completely understood everything, so that's great. But what I want to do is kind of take you through what I learned along the way and have learned since, and it might clear up some things for you. I saw on the Slack channel some of the confusion, so I'll try to also target it towards those areas. But I don't want to kind of repeat a lot of content that has, like, for which there's already great resources out there. I mean, the Qiskit team and resources and documentation is really amazing. And their YouTube videos and their summer school lectures and everything together is like kind of mind-blowing how all of that content is just freely available and just such an engaging open source community. So yeah, I don't want to redo anything that's already been done very well, but I just kind of want to bring everything together, and I'll probably point you to some resources that were very helpful to me. Just a quick disclaimer: I'm not a chemist, I'm not a physicist, and I maybe can barely call myself a computer scientist. But so I'm not an expert in these areas. So if there's any inaccuracies or things that could explain better, please do leave me a comment and provide some feedback if you'd like. Yeah, I'm totally open to that. That would be great, and maybe make future videos like this even better. Yeah, but if I point to any resources, I'll call it out in the description. So let's start with this slide here. This is a way I've kind of mapped out the overall problem structure. It's, I guess, similar to the one in the exercise 5 notebook, but just the way I think about things. It kind of makes it easier for me to see. So let's go through it. And this stuff is as much for me to refresh my knowledge as it is, might as well share it with everyone, right? So I've kind of got this slide here divided into two sections. One is the setup of the problem, the VQE, or the Variational Quantum Eigensolver. And on the left is the kind of execution once you've set it up. And so there were a lot of struggles in both areas, but I think especially the setup is important to think about the theory behind it. Yeah, so on the setup side, right, basically what we're trying to do is define a Hamiltonian in terms of a basis that can be mapped into qubits. And so you see the two main sections here are defining the electronic or fermionic Hamiltonian, which works in the basis of molecular orbitals, right, where the electrons are residing in space. But we can map that onto spin orbitals, which are more appropriate to map to qubits, because the math of how the Hamiltonians and the operators involved commute, they're like commutative properties, are different in the spatial basis as with the spin basis, and so you kind of can't do the math you want if you don't convert it to a spin orbital basis, as in you won't be able to use a quantum computer or a quantum circuit to do the math you want. Yeah, so within the electron Hamiltonian, right, we are going to go through the steps of selecting the molecule, which in the exercise 5 we use lithium hydride. And then we need to set up the electronic structure problem. And we'll talk about some of the useful tools that we had, like freeze core and remove orbitals. And then we want to use the Hartree Fock method to get the second quantization of the system, which is basically just a way of expressing the system in terms of quantum mechanical field operators. So we'll talk about that in a bit. And so once we've defined that, right, so nothing here is anything quantum yet, then we're going to convert it to a system that can be commuted in quantum mechanical terms and translated to qubits. So you can map the states using some of these parity mappers, Jordan-Wigner mappers, Bravia-Kitté mappers. And there are some things you can use to reduce the problem even further, like 2-qubit reduction and Z2 symmetry. So I'll talk about those a bit. But after that, once you've set up your qubit Hamiltonian, what we're ready to do is set up our quantum circuit and also do the classical calculation of the ground state energy. So this is like the ground truth that we're going to use in our optimization, kind of like try to converge towards this value. And you may ask, like, why go through any of this if we can just calculate the exact answer using classical methods? And so the answer to that would basically be that, you know, VQE is still an active area of research. The point is that in this exercise, right, we chose lithium hydride, for which it's quite trivial to calculate the ground state energy of that molecule. But for larger molecules, it becomes increasingly hard for classical computers. And so by having this kind of setup, we can kind of learn the relationship between what a quantum circuit should look like for a particular molecule, maybe the methods to create a circuit based off just knowing the molecule information. And so that for larger molecules, when we scale this system up, and we can't rely on classical calculations, we have some degree of assurance that we understand the methodology for creating the appropriate quantum circuit and then can use it moving forward. So yeah, still a lot of research to be done there, but a lot of great work and effort being done there. So yeah, so within the quantum circuit, right, we actually use just the Hartree Fock method to initialize the state. This is the Qiskit method. So it'll just give us an initial state. And then what we need to do is run that state through what's called an Ansatz. And so it's just kind of the structure of the quantum circuit, the kind of landscape that you will do your computation on, to which once you run through a classical optimizer, which can take care of the parameter tuning. You can keep going through, try to converge towards the ground state truth classically calculated, and that's how we will arrive at the ground state energy using a quantum circuit. Yeah, so the classical optimizer takes care. So, okay, back up the quantum circuit, right? It basically, the ansatz will consist of single qubit rotations and entangler maps. And so when that's fed into the classical optimizer, right, it will see how close it got to the solution. And based on the error or loss function, it will update the parameters, which is essentially the single qubit rotations. Then try again and move towards the direction where it's getting closer to the ground state truth. And so there's different kinds of optimizers you can use, like think of it like just stochastic gradient descent or something like that in classical machine learning, but there's a lot of tools out there. And so, yeah, so that's the overall problem setup. But let's dive into more details. So the first step is to select the molecule. Yeah, quite simple. So if you look at the exercise 5 Qiskit code, right, it basically has this string to represent lithium hydride and its spatial coordinates. For this particular configuration, you can load other kinds of configurations. And so that's basically just how we set up the molecule. And all of these are different tools you can import from the Qiskit library. I won't get too into that. Just take note that sometimes I don't know if they're kind of deprecating or transitioning drivers or something, but this PySCF driver can cause problems. And if you kind of do it outside the exercise or the IBM Quantum Lab notebook, if you try to do it yourself, you might run into some issues. Yeah. So the next step after selecting the molecule is to set up your electronic structure problem. So I think this is where some of the theory really started to come in, and we all started to have some issues. Well, not all, but me at least. So let's look a bit at that. If this slide looks intimidating at first, it's actually really simple when you break it down, so bear with me here. So what we're trying to do is set up our Hamiltonian operator, electronic 1, so that's represented by this H hat. And so if we split it up, we're looking at the sum of the kinetic energy plus potential energy. Just normal physics stuff, right? And so we can break that up for an atom into the kinetic energy of the nucleons, so the particles in the nucleus, and the electrons. And then we add the potential energy of all the possible interactions. So the nucleons can interact with each other, the nucleons can interact with the electrons, and the electrons can interact with each other. This is the part that makes everything difficult and complicated, but we'll come back to that. So, if you kind of have seen the Schrödinger equation or just general physics, right, you can recognize that the kinetic energy is the h bar squared over 2m times the del or nabla operator, not really squared, but the second, in a rough way of speaking, derivative of the quantum mechanical wave function. You might recognize this. Bit of intuition behind it, right? Like the h bar squared del squared operator. If you take these together, it's kind of the momentum squared. And so you kind of have momentum divided by m, which very roughly speaking is like the velocity. So I'm just trying to kind of relate this to half mv squared, to roughly speaking. This just for some intuition. This is not exactly what's going on here, but that's kind of like the analogy. Yeah. And then the potential energies are basically the Coulomb equation, where I've denoted like E as the charge of the electron, either plus or minus, depending if it's attraction or repulsion. And then, where sigma naught is like the permeability of free space. Yeah, so there's that. And so if we apply these, substitute these into the T and V terms, we'll get this huge, complicated looking thing. But we can simplify it by converting to atomic units. We basically just set a bunch of things to equal 1, which we can always just remember and convert back later, depending on the units that we want. So, if we take this whole thing we can simplify to half 1 1 1. Yep, and basically we're taking the mass of the nucleons and electrons to kind of be constant, so we don't really need to account for them in each of the summations. Yeah, as well as the charge, all these constants we're kind of just simplifying to keep the math cleaner. That's what we're doing in this step, right? And so, but just to quickly relate the equations, right? Like kinetic energy of the nucleons is the sum over, so the capital letters are kind of nucleon indices. So it's the sum over the kinetic energy of all the of each nucleon. The sum of the kinetic energy of each electron. The sum of the interactions between each nucleon, the capital letters again are like nucleons. Some of the interactions between the nucleons and electrons, capital and small I, and the sum of the interactions between each electron. So if we can even go and simplify it even further, right? If you think of the nucleus of an atom, it's quite stable. It doesn't really contribute to the possible changes in energy configuration. So we might just, in the Born-Oppenheimer approximation, right? We can just remove those terms. It's just a lot to carry around in the math and not really useful. You could always add them back in later if you want the total energy of the system, since they're not really going to be changing depending on our configurations that we're going to explore. So we remove the kinetic energy of the nucleons and the interaction between nucleons. And we're left with this 3-term equation. So I think that's not so bad. And that's what we call the electron Hamiltonian. Or the Fermionic Hamiltonian. But it's electron because kind of removes the nucleons. And so this resource here, right, this TMP Chem, especially the Hartree Fock theory playlist, is really just amazing at explaining all of this. I highly recommend it. It's a long playlist, but you can select the videos that are more relevant to your interests. It's super good. I can't recommend it enough. He did a great job, and that's how I got the idea, which I tried to simplify a bit more here. Yeah. So let's take a quick look at energy levels. Not gonna dive too deep, but just to get an idea of the chemistry. I might be diving into this a little too far, but I kind of got a little carried away. But anyway, so if you remember from some of your introduction to chemistry classes, right? Like electrons don't really follow the simple Bohr model of the atom, but they rather occupy orbitals at different energy levels, and the energy levels kind of go up depending on the orbitals that are occupied. And so an s orbital is like a by the way, this picture, I just thought it was too good to not include, but I don't really know where it's actually from, so I can't cite it. But I found it in this Stack Exchange post. Yeah, so so each orbital, take note, has 2 electrons. It can be occupied by 2 electrons, so that's why I've represented it as 2 electrons here. And then some orbitals have multiple configurations that can be taken up. So each of those configurations can also take 2 electrons. And so like the red s orbitals is a spherical shell. So by the way, the shell kind of represents the probability, the space in which there's a high probability of finding an electron if you measure it. It's not saying that it's there, it's not really saying that it's in a, I don't want to go too far to say that it's like in all those places at once, but it's, because I don't like that way of speaking, but it's just that if you measured it, you'd likely find it in this region. And I think most people, when they draw this, they draw like a 90% confidence bound, where you have a 95% chance of finding it within this boundary. So that's what the boundaries and geometries are. So yeah, red is this spherical shell. The orange ones represent these P shells. So there's 3 kinds of configurations you can have. And an electron, as it moves up, will eventually have to occupy all of them. And each can be occupied by 2 electrons. Then we have the blue ones. They also all take, there's like 5 different geometries that it can take. And the green ones, so they're S, P, D, and F. The green ones are F, and they have 7 different kinds of configurations that, can be occupied. And these are, I guess these geometries are very, very interesting. I want to look more into them, but at a high level, roughly speaking, I think they kind of arise as these geometries arise as a function of the energy and spatial constraints and boundary conditions within the atom. And so it'd be really cool to look at how these geometries come, but that's outside the scope of this. So yeah, so let's say we have a situation where you know, the 1s, 2s, 2p, and 3s orbitals are fully occupied by electrons. You know, and these are kind of potential places where electrons can fluctuate too. And so, you know, it might look like this, it might look like this, and things might go back and forth. Yeah, and so we're kind of exploring this configuration space to find the ground state energy depending on all the interactions between the electrons, as we noted, as well as like underneath this, all of their interactions with the actual nucleus. And so if you notice, right, the bottom part here is not really fluctuating too much. They're kind of stable there. So another way we could simplify the problem or the space that we're exploring is to freeze the core. So this core isn't changing. It's a very low likelihood that it would change given the whatever configuration we were in. Maybe it's not always applicable to every configuration, but if there was a core to freeze, it's kind of recommended to do it. It can simplify the problem space. So now we don't have to consider all of this. You can also remove certain orbitals, right? Say like the energies associated with this problem will never get to the highest orbitals. Then why keep them around in the math? You know, they're just heavy to keep around, so we just completely remove them from consideration. Yeah, and so we can reduce the problem to like this small space here. Now, at least in the exercise 5 challenge, I noticed that the orbitals I removed, which gave me the best results, were also some in-between orbitals. So I don't know if there's kind of some constraints that sometimes make it almost or unlikely to fill a middle orbital. Yeah, but so you can just explore and see what gets you the best results. So maybe I also want to take a minute to illustrate why this problem is very hard, right? So if you see these remember the term I told you, the electron-electron interaction, is what makes the problem hard. So it's kind of illustrated here. Like if you see, right, the energy of this electron, it kind of depends on its interaction with all of these other ones. But each of them also depends on the interaction with all of the other ones, and each of them also interact. So it's kind of like this circular thing where this one depends on this one, depends on this one, depends on that one, depends on that one, depends on that one. And so this is kind of like a classic analogy to like the 3-body or many-body problem, where when you had 2, it was fine. When you add in the third one, they're all dependent on each other. So there's no computationally reducible way to just have like an equation to describe it. You kind of need to do like a numerical analysis of it, have a starting guess, and iterate over that. Some of the best way we know how now. So this is where our quantum computer is going to kind of help us, but basically that's what makes the problem hard. Yeah, so so let's move on. So just a summary of what we've done, right? We've really simplified the problem. We started with this long, intimidating equation here. We kind of removed the nucleon-only terms. And we even further simplified by freezing the core and removing certain orbitals that we don't need. Yeah, so the nucleus is only here for its interactions between each electron. And so, by the way, all these things that you remove, like when you freeze the core, right, of course your overall energy will be less, but since it's an unchanging value, you just throw it back in later. And so this is something that people also missed on the Slack channel, but it was an easy clarification. That when you freeze core, you have to account for that when you submit your answer. Okay, so now let's look at the Hartree-Fock method. And so we kind of expressed our electron Hamiltonian like this, but we need to transform it into a notation or matrix form that we can kind of work with, because like for example, what I told you about this problem was hard. We can't really compute this unless we have it in like a different basis, which I'm about to show you here. So you can see that, you know, if you're familiar with your bracket notation, that this term here is equivalent to this. So what we've done is introduce these creation and annihilation operators, and essentially what they do is they represent moving electrons around. So like okay, in kind of quantum mechanics, right, you not only have to consider where you classically think the electron is when you're doing this hard problem of finding the interaction between all of them, but you also have to think of where it could be, which is kind of weird, but it's like, you know, this electron is not necessarily in this orbital, but has a probability of being in this orbital, and a certain probability of being in this orbital, and a certain probability of being elsewhere. And you have to consider all of those because it's not really defined. And so, sorry to jump around, but what those creation and annihilation operators do is they kind of pick them up and put them somewhere else. And so you can consider all of the possibilities based on their probabilities of where they could be. They all need to be factored in to give you the total energy. The quantum mechanics doesn't work without doing that. It's just like this weird property of nature that we've stumbled upon, and kind of, you know, maybe we're getting more and more of an intuitive sense of why that nature is like that, but for now let's just say it is that way. So since it's not in a defined position, you have to consider all the positions it could be in. Yeah. And so this term you can also see translates to this term here in the basis of the creation and annihilation operators. Yeah, like I said, they just act to move the electrons around as part of the consideration of the total energy that they're contributing. So you can see the inner summation term is and the inner product of the electron bases. And you see, so I think a key thing to note here, because the notation is really confusing. It took me a long time, but each thing that was only a small I here, now we're looping through I and j, and that's to support the creation and annihilation operators, to move the electrons around and see the different possible configurations. Yeah, so like each I became an ij. The big I's are fixed because that's like the nucleon, but the small I's like became big I's and j's. So here we had an I and a j, right? So now the I has to expand to an I and a j, and the j has to expand to a k and an m, which makes it look very confusing. But maybe you get the idea now that it's because we're trying to see all of, for each I we need to see each other I or a j that it could have been in. Rather, for each I we need to deal with another k that every pair of electrons, right? So each thing that here was just an I, we have to consider each pair that it could have been part of. And so that's how we end up with the electron Hamiltonian expressed in a different way for the Hartree Fock method. And then, you know, we can combine these terms since they have the same sigma operator, and they're just can be linearly applied. The same annihilation operators into one term here. So this is what we call the one electron integral. And so I'm just trying to bridge some of the notation you might see around in the Qiskit and other documentation. So this represents this one electron integral you'll see here. You can see it's a similar structure, and I'll let you look into it. But and yeah, this is what it represents. And this is a two electron integral. Which, you know, it looks like this. And so you can see how they have a similar form. And so the total energy Hamiltonian electron Hamiltonian kind of looks like this. Yep. So this is how they all link to each other. I was super confused when I saw these different things. I didn't really get how they are together, but again, TMP Chem on YouTube, the Hartree Fock theory playlist is amazing for all of this. And actually, in general, for any kind of chemistry or computational chemistry, anything like that. All right, so in Qiskit, everything I just went through, I probably babbled way too long, but the whole electronic structure problem is done in one line here, even freezing the core and removing certain orbitals. And then the second quantization of the system that I showed you is done in this line. And yeah, so then we have our electron Hamiltonian taken care of in like 3 lines. Probably took me like 20 minutes to just explain. Yeah, so then what we have to do is the important step of mapping it to a qubit Hamiltonian. So I think this diagram was already really done really well in the Qiskit documentation, so I'm not going to reinvent it, but you'll recognize this here, which I just showed you in a previous slide of the electron Hamiltonian in the Fock state basis from Hartree Fock. I don't think I said that, but yeah, this is the Fock state basis. And you can see, right, this is how the creation and annihilation operators work. If the indices are the same, this is how these kind of terms come out. So there'll be 0 unless, you know, we take the conjugate of each other. But anyway, so there's a different way of just kind of showing the energy levels that are occupied by the electrons. But what we need to do is convert this spatial mapping into a spin mapping. And so there's many things you can do. The one shown here is Jordan-Wigner. So for each annihilation operator, we would basically take this kind of this tensor product, I don't want to call it summation, but product over each term and convert it like this. I'm not going to dive exactly into the math, but basically what this does, it changes this setup so that this is still representative of the original setup, but it commutes. It has the commutative properties of that can be represented by qubits. And so, you know, this video here was really good at kind of talking about almost everything that I've talked about so far. It was from the Qiskit Global Summer School last year, 2020. And yeah, it's a bit fast if you look through it, but if you take your time, maybe with some of the things I've shown you, you might get an idea, but I do recommend it. And so if we look at some of the Qiskit documentation, right, from this link, I just kind of want to show you, I've shown you a lot of non-code stuff, but let's look at the code. So if we print out that second quantization Hamiltonian, we get something that looks like this. It's in like this plus minus in basis, right? Everything is expressed in terms of in plus and minus. And then we have the summation of those. But what we want to do is transform it to a qubit Hamiltonian. So we use this qubit converter, and this particular one uses the Jordan-Wigner mapping. And now we express it in terms of the I, Z, X, and Y basis. So you'll probably, you know, recognize these as the Pauli gates, rather Pauli bases, but yeah. So you know, there's like identity X, Y, and Z. I think you'll be familiar with those, but if not, you know, look up the Qiskit textbook, which is, by the way, another really amazing resource. So yeah, you can see how We've totally changed the basis. It's still representative of the problem, but it allows us to use the quantum circuits that we will set up. And so, I think I'm talking too much, so I'll speed up a bit, but yeah. And you can also watch this video at like, 2 times speed. And so I just wanted to show here that, if you use like a different kind of mapping, like a parity mapper, and use this 2-qubit reduction, which kind of searches for symmetries in the original problem. Symmetries are always a great way to reduce a problem because you don't have to carry around the information, because a symmetry is almost like a redundancy or repeating something that you can just throw back in later. It doesn't change as the problem goes along. And so, you can go from this huge mess to this really nice compact representation here, which makes it easy to represent in a quantum circuit. Yep, and so this is kind of the exercise 5 notebook that I had. We used or at least I used a parity mapper. We used 2-qubit reduction, and there's another Z2 symmetry reduction, which further reduces the symmetries. And for this, I recommend lecture 26 of the last year's 2020 Global Qiskit Summer School. This was a really amazing lecture. I think it's 25, 26, and 27, which I thought were great, but this one is particularly focused on this part here. But while I was doing the challenge, I think that I was like getting a bit frustrated that I couldn't figure things out. But this is what brought me back. I think the lecturer here is really great at breaking it down and explaining it in a nice, calm way. And so I really learned a lot from this. I do particularly appreciate the few lectures around this one. But of course, all of them are great. But just for this problem, this is what kind of brought me back. And so, yeah, you can see that, in the original Fermionic Hamiltonian, we had like 117 terms. The first term kind of looked like this, expressed in this plus minus plus I basis. And then when it's converted to a qubit Hamiltonian, it had 100 terms and it looked like this. So we kind of reduced the number of terms using 2-qubit reduction and symmetry reduction, Z2 symmetry reduction, before starting our problem. So if you look at the untransformed data, right, we had 3 particles and 12 spin orbitals. But when we transformed it, we end up with 2 particles and 6 orbitals, just to show you some of the changes along the way and how this might really become beneficial at scale. Yep. So now we've done the qubit mapping, and so kind of everything up here was classical. We mapped it to a state. Now we're ready for quantum stuff. So, or rather quantum computing stuff. So if you use the Hartree Fock method inside the Qiskit library, it will initialize a Hartree Fock state for you. And so this is what we're going to manipulate to try to arrive at our ground state energy. And so we're also ready, using all this information, to calculate the ground state energy, or the ground truth, which we're optimizing towards for this particular problem. And so what this problem boils down to is, okay, you'll be familiar with this Fock state basis electron Hamiltonian now. And so what we're doing is essentially an eigenvalue problem. So we have our electronic Hamiltonian, and when it's applied, or I like to think of it like stamped onto our wave function, what we'll get is the total energy of the system. But that turns out to just be a matrix, which is kind of the same as applying a scalar to the wave function matrix. And so what we can get is eigenvalues, which represent the possible like stable energy configurations that this Hamiltonian and wave function setup can kind of settle into. if you're familiar with eigenvalue problems, you'll see this, right? I used to always just be like, I mean, this side equals this side, so doesn't H equal E? But the difference is that this is a scalar and this is an operator or a matrix, and so this represents some of the stable configurations that this can arrive at, in a very approximate way of speaking. And if we take the lowest eigenvalue that we get out of this, the E naught, we can solve it using, you know, Dirac notation manipulation like this. And so we will get the minimum energy eigenvalue state. And this can be computed classically for a trivial system like lithium hydride, but it's much, much more difficult at scale for larger molecules. And so basically this comes down to diagonalizing the matrix. So we can use these Qiskit tools, like our NumPy and Qiskit tools, like the NumPy minimum eigensolver factory and the ground state eigensolver in Qiskit. And then we get this exact electronic energy. So yeah, you see, if you didn't freeze the core, you'd probably get a much higher number. I remember, I think it was around like much higher in magnitude number, like minus 8.7 something, we'll see at the end. But because I've frozen the core, we're only dealing with the electrons now. Okay, and their interaction. I mean, we're only dealing with a certain active space, not the core. And so yeah, the energy is lower. But this is the value we want to kind of optimize towards in this problem. So now the next step is to set up our ansatz. And so, you know, in the exercise 5, they gave us a template to try to do that. You know, you can use different types called like toLocal, UCCSD, PUCCD, SUCCD, or you can even customize your own. I think in the notebook they did a great job of explaining it already, so I won't redo that. This is a screenshot taken directly from the notebook. But maybe some of the major points is that basically what we're essentially doing is applying single qubit rotations. Doesn't have to be all of them, but just whatever you feel is correct, and then doing an entangling mapping. So essentially you want all of the qubits entangled. They don't all have to be entangled to each other. You can kind of do that, like if you want qubit 0 to be entangled with 1, 2, 3, and 4, and qubit 2 to be 0, 2, 3, and 4. You can do that, but it's kind of usually overdoing it. But you at least want them all to be entangled to at least one other qubit. Yeah, and so this shows you like the different kinds of configurations that people are like actively researching. Inside the notebook, they have a lot of great links to some research papers of how these were developed. Yeah, but essentially these theta parameters here are what we're going to optimize. So basically the rotation of the single qubit rotations are what we're optimizing, and they're parameterized by this parameter theta, or these parameters theta. So once we run it through this this circuit of rotations and entangle mapping, by the way, this is the solution that I arrived upon, pretty much just through trial and error, to be honest. And so yeah, 0 is mapped to 3, or C naught to 3, 1 is C naught to 0, 2 C naught to 1, so we have a full entanglement here. By the way, you recognize this was our initial state that we had when we did the initialized Hartree Fock theory, and then we have these rotations. So that's what I arrived at. You can play around with a lot of things. I think some things that people missed were that for the entangle maps, right, you can customize your own. You don't have to choose the default ones like circular or linear or whatever they were. This is what got me to the answer. Like without this, I wouldn't have. So I used the toLocal setup with a custom entangler map. Yep. So I think that's all for this part. But this is the heart of the problem, right? Like finding this ansatz is what's critical to be able to solve the problem. And so I can't really say that there's a defined methodology of finding it. This is like one of the main active areas of research in VQE. And so, this is an important problem that I guess you guys could also work on if you're interested. And this exercise was a demonstration on how even for such a simple system, a lot of us might have struggled. Yeah, so there's no one size fits all for this, at least yet. And then we, as I mentioned, right, those single qubit rotations are the parameters that we are optimizing. And so we'll feed our quantum circuit, the output of our quantum circuit into the classical optimizer, as well as the ground truth, because that's what we're optimizing towards, and we'll keep updating theta until we converge towards a ground state truth, or at least with some error that we are accepting of. This is where we make our magic happen. And so, there's different kinds of optimizers you can use. Think of these as like the different stochastic gradient descent or whatever in normal classical machine learning. There's different ways that you can tune your parameters to optimize your solution. And so the final step is represented here, where we call all of the functions required to do the VQE optimization. And you can see this is like, I use the Qubit parity mapper the Qubit optimizer. And I had a parity mapper and I used the two local ansatz. And so you can see that it quite quickly found, like after about 40 something iterations, the exact electronic energy from the classical calculation with only 3 C-naughts, which was the rank 1, meaning like the best possible solution, which I think like around 200 people got in the challenge. And that's pretty much it. And so yeah, when you submitted it, if you guys got to this point, it probably felt really great. And just as a quick note, this is what I was talking about, the freeze core part. You need to set it to true if you did, otherwise, your answer would be off by the core that you froze, the amount of the core that you froze. And so just as a final thing in the Slack, I would like to repeat some of the notes that I kind of gave. I thought it might have been helpful to some people, but it's crucial to understand the electronic structure problem documentation. I think a lot of struggles were also not even the understanding of the theory, but some of the documentation. And so I know it's hard to gather everything that you need to know from that documentation, but it's worth taking the time to try to understand exactly what's going on. Otherwise, you'll probably spend even more time just trying to naively guess of what's going on. And so it took me and people a long time to figure out that you can actually pass the freeze core transformer object into the electronic structure problem. Yeah, and I also was noting that if you keep getting stuck, you need to also make sure your exact electronic energy value was correct. Otherwise, you're probably optimizing towards the wrong value, and that your ansatz, right, might not be giving enough breathing room for you to find the solution. So you need to really understand the parameters that are in there in the documentation and play around with them. Like for the specific example of my entangler map, right? If you just use two local and switch between circular and linear or something like that, you may not, or I may not have found the answer. When I really looked into the documentation, I realized I could make custom entangler maps. And since I was so close to the solution, I was like, it might just be some other combination of this entangler map that I don't have a default variable for. And so I found one and it kind of worked. I know it's a bit of guess and check, but sometimes you have to do that a little bit in computer science, especially in an active area of research. Like just a really, really huge thanks. I'm super grateful for all the IQC mentors and the whole like Qiskit community in general for putting this together. I mean, the notebooks were of like really, really excellent quality. as well as all the documentation and resources out there. They really put a lot of time and passion into it, you can tell. And I think in particular, these 3 lectures from 2020 were fantastic on YouTube, particularly for this problem. And so, yeah.